classes.
Right. Okay, max and mins. That is where we are going. We are going to start graphing everything. Polynomials, rational functions, all of those things that we did back in college algebra and we graphed. We are going to graph them again, but we're going to be more accurate this time. Back then we were pretty limited, like we found where the zeros were, but then beyond that we just kind of estimated the graph. Well, now we're going to find like the actual maximums and minimums and how the graph should be curved and all the different attributes of it to make those graphs more precise. So, kind of the motivation here. These are used in optimization problems, which is a big feature of why so many people have to have calculus as for their degree. One situation, optimization, what shape of a can would minimize manufacturing costs? If you are going to be manufacturing something, you want your cost to be as low as possible, right? So you need to minimize your costs. The maximum acceleration of a space shuttle. Medical application. What's the radius of a contracted windpipe that expels air most rapidly during a cough? Seems very fitting right now. At what angle should blood vessels branch so as to minimize the energy expended by the heart in pumping blood? So these are all kinds of optimization problems. Today we're going to focus on different kinds of maxes and mins. Remember, we've talked about them before, local versus absolute. Absolute or global maxes and mins are the highest or lowest on the entire graph. On yours, I condensed this. It's all on one slide. So these are highest or lowest on the entire graph. We can write them as ordered pairs or function notation. F of 3 equals 5. That means my highest point is 5 when the x is 3. Okay, that is my absolute max. It's the highest on this entire graph. We are assuming these are endpoints on this graph, by the way. 2, 6 is my lowest point, so you could write it as an ordered pair or function notation. Absolute max and min might be called global. Just be aware those are the same. In general, maxes and mins are referred to as extreme values. So if I say find the extreme values, that's all maxes and mins. One thing to note, absolute max and mins can be endpoints. So if you're looking for the highest or lowest on the entire graph, you do want to consider your endpoints of the graph. All right. In contrast, local maxes and mins are higher low points, but not necessarily the highest or lowest on the entire graph. They are just higher or lower than the surrounding points. So like this is not the highest on the graph, but it's higher than the points on both the left and the right. So that is a local max. What would this one be? It is an absolute max, and it's also higher than the surrounding points, so it's also a local max. This one is both. What would this be?
Local and absolute min.
Oh,
It's not absolute min.
Yeah, this is just a local min.
I was not looking.
I know you were looking at this one. This one is also just a local min. Endpoints cannot be local maxes and mins. So local max and min cannot be an endpoint. Is Josie here today?
No, she's gone.
I just need. I have to send this to them. Thank you. Do you guys understand the difference between local and absolute? This is just another one showing us local min, local max. This one is both local and.
Have we done this before?
Yep, we
Okay.
did it in college
Okay.
algebra. Okay. So if I were asking for the maximum or minimum values of f of x equals x squared and identify it as local or global. We know what x squared looks like, right?
Mm-hmm.
What is it?
Parabola. Opening parabola.
Okay. If I put in 0, we get out 0, 1, 1, 2, 4. 1, 2, 4. So that's what my graph looks like. Okay. What are my maxes and mins?
Low absolute max.
Okay, why don't I have those?
It goes to infinity.
Right, just keeps going up, so there's no single point that's the highest. Do we have any local max? No, so there's no local or absolute max. Do I have a local min?
Yep.
What about an absolute min?
Yep.
Yeah, they're the same. I'm just gonna call it local / absolute min, it's both. And you can either write it in function notation, f of 0 equals 0. If you give me the point 0, 0, that would be fine as well. Don't just tell me 0, tell me the x and y values. All right, what about x cubed? All right, x cubed is our share. Does it have any?
Just the 0, 0 thing.
Is
Oh
that-
no, it has 3. No, it doesn't have 3.
Because it keeps going.
I always draw these pointier than they're supposed to.
Oh. Yeah, this one has no maxes or mins at all.
I always give them like a little.
Oh, you give them a little.
I thought they're a chair. They gotta have a place to sit.
Well, even if you flatten it out a little more, it's still not technically
Okay.
higher or lower. But if it did like a little number like that, then you would have a max and a min.
A little one of these.
Yeah. Okay, let's look at a graph. And I apologize. I tried to like screenshot this out of the book, or maybe I tried to draw it. I don't know. But it's not high quality. Forgive me. All right. So when I'm looking, do we have an absolute max? Is there a highest on this entire graph?
Yes.
4, 3. Do you want them as, do you care if I do function notation? If you don't like that, you can write it as an order pair. I don't care. Do we have an absolute min? No, because I look, here's my low point, but it's an open circle. And open circles don't count, so there is none. Okay, local max. These exclude endpoints, and they're higher or lower than surrounding points. So would my absolute max count as a local max as well? Yeah.
Oh yes. Nice.
Because it's not an endpoint. Okay, what other high points? So right here's a high point, but what's wrong with it? It's open. Here is a high point. Is that higher than the points on the left and the right of it?
Mhm.
Yep. So it doesn't matter, that's a discontinuity there. So f of 0 equals -1 is an a local max. Any others? Because if I look here, this is higher than the points on the left, but not the points on the right, so that's it. Okay, local min. Low points.
-2. -2.
I think it's -3. -2, -3.
Yeah.
Okay. This one, can it count for anything?
No.
No, it's open. Can this count for anything?
No.
No, it's open. Okay, is this lower than points on both sides? No. We can't count endpoints, but we are missing one. This dot. This dot, it's not continuous, but it's a dot on the graph, and if you go to the left and the right, is it lower than both of those? Yes.
4, -2.
So -4, -2 is also a min. All right, let's draw a graph to meet some requirements. An absolute max of 5. That means it is the highest on my entire graph. Did I tell you the x value? No, so it just has to happen somewhere. Can it be an endpoint?
Yes.
Yes, absolute could be an endpoint, doesn't have to be. The absolute min is 2. So somewhere I hit a lowest point of 2. Again, did I tell you where? No. Oh, hold on. I'm reading this backwards. I said an absolute max of 5. That's not what it said. What did it say? At 5. If I read the words on the paper instead of the words in my head, it helps, right? So I said at 5. When x is 5, we have our high point. Did I tell you what the high point was?
No.
No, it's just somewhere. And my lowest point is when x is 2, because I said at 2, not of 2. There's a difference.
Weird.
Okay. A local max at 3. So when x is 3, we have our highest point. But not for, or just for that area, not necessarily the highest on my entire graph, right? So 3 somewhere, and we have a local min at both 2 and 4. So 2, can it be an endpoint? No, because it has to be both a local and an absolute. So I'm going to come at 2. 3 just has to be a local max. Okay, I didn't tell you how high it was, but we're going to hit that point. If it's a local max, we have to turn around. I have a local min at 4, so when I get to 4, we have to turn around and come back and hit at 5. And that is an absolute, so that has to be the end. Now, is this the only such graph? Absolutely not. This is just a graph.
What is that? Is that point on the endpoint relevant on the left? Like,
No.
It doesn't matter what it is.
Nope. Just as long as it's not higher than the max or within the min. Alright. So now let's talk about how we can actually find these if we're looking at a function. If you have a continuous function, then it has to have both an absolute max or min on a closed interval. So if it's continuous on a closed interval, that means it has to have closed circles at both the open and end, or the beginning and end. And if it's continuous, we have to have a max or min somewhere in there. Okay, it doesn't have to have local, but it has to have absolute. It only works if it's continuous. These are a few examples of how that might work. If it's not continuous, though, would I have to have both? No, because this one does not have an absolute max because there's an open circle there, or asymptotes. So this idea only works for continuous functions. If I want to find them, we're going to stick with the nice functions today, the continuous ones. If I wanted to find these, what would I be doing? And setting it equal to? 0. The derivative is the slope of the tangent line, right? If it's a max or a min, you have a horizontal tangent line. So we're really looking for points where the derivative is 0. That's all we're finding here. Okay, and that is actual theorem. If it's a max or min, the derivative is going to be 0. One thing to question, if I find a place that the derivative is 0, does it have to be a max or min? So if I think about x cubed, we already said it doesn't have a max or min, right? What's the derivative of x cubed?
3x squared.
If I set that equal to 0,
You get 0.
we get 0. But is 0 a max or a min? No. So, we can find a place where we might have a max or a min by finding when the derivative is 0, but it doesn't guarantee. The derivative can be 0 without a maximum or minimum at that point. I also want to look at this one. Absolute value. Can we all agree that there is a minimum right here? Alright. But when we do the derivative, okay, anytime we've done the derivative, we've dealt with absolute values, we first had to rewrite it, correct? Absolute value, the definition we always use is it's x if x is greater than 0, and it's the opposite of x if it's less than 0. If you do the derivative of that, what's the derivative of x?
0. I mean 1.
And what's the derivative at negative x? Okay, So if I'm thinking about this, my derivative, it's 1 for the positives, -1 for the negatives. Does it exist at 0? No. So that we found, just because the derivative is 0 doesn't mean it has to be a max or min. Here there was a min, but the derivative does not exist. So what we are going to have to do, these places where the maxes and mins happen, it's when the derivative is 0, or in this case our derivative was undefined. These numbers where the derivative is equal to 0 or undefined are called critical numbers. So when we are finding maxes or mins for a function, what I'm going to ask you to do is find all of your critical numbers. So that's anywhere your derivative is 0 or undefined. Then we are going to test those to figure out which ones are the maxes and mins of our particular function. So let's just jump right to it. Alright, first we're just going to practice finding critical numbers, and then we'll do an example where we actually get the max or min from that. Alright, if I were going to do this derivative, what might make it a little bit easier?
Yes, that might.
I would maybe even just
Yeah. I
distribute.
thought that's what standard was.
So that would be 4x
Yeah.
might have meant,
Yeah.
yeah, I think you knew what you meant. This is an x to the first, so 1 plus 3 fifths would be 8 fifths. So then if I do this derivative, that's 12 fifths x. What's 3 fifths minus 1?
Maybe 2 fifths.
Minus 8 fifths x. What's 8 fifths minus 1?
2 fifths.
Alright. If you don't like the negative power does what?
Puts it on the bottom.
So to find my critical numbers, I need to know anywhere this derivative is 0 or undefined. Is there anywhere you can tell me it's undefined right now? Undefined is like what x cannot be. Okay, because x is on the bottom right here, can we agree that x cannot be 0? So that means my first critical point is when x is 0, because the derivative is undefined. If I plug in 0, it does not exist. The rest of them, we have to set our derivative equal to 0. I'm going to add it over, because then what did we do?
Multiply by here. Oh, yeah.
40 x to the 2 fifths and x to the 3 fifths is just x. So divide 60 over 40 is 3 halves. So my critical points are x equals 0 and 3 halves. Those are the places where either the derivative is 0 or undefined.
So you just plug those numbers in, which one's high, which one's low?
Look at you already convinced. Is that okay? So that's how we find our critical numbers. So to decide what our maxes and mins are, we have to find our critical points. Then we are going to plug the critical points and the endpoints into the interval. And those, then the biggest Y value is our absolute max and the lowest is our absolute min. Does this give me local maxes and mins? No. But this will give me my absolutes. So that's just what we're going to practice the rest of the hour. So if I gave us this one, I want the absolute max and min. So what do we do first? It's 3x squared minus 6x. And I need to know when this is 0 or undefined. Is this ever undefined though?
Mm-mm.
Okay. So if I set that equal to 0, factor out of 3x. And I get what?
0 and 2.
Okay, first check. They have to be in the interval. It's possible that they won't be. Are both of those on the particular interval I want?
Yes.
So what I'm going to do is take my endpoints, because absolute maxes and mins can happen at the endpoints, and my critical points, and I have to plug all those numbers into what? The original function to decide which one's the biggest and which one's the smallest. Okay, so you can use a calculator here. Let's plug them in. I'll be nice, I'll do 0 for you. I've got mine done. Two is -3. Somebody do -1 now.
I got point
Yeah, 0.125 or 1/8. Okay, so what's my absolute max?
17.
Yep, so f of 4 equals 17. 4 is 17 is my absolute max. What's my absolute min?
0.125. Or no, -3 is not.
So I got my absolute max and absolute min. It's a good
At this point, we've almost finished up here. At this point, we're almost done.
Just take it.
Bite it off this guy.
Alright, let's look at another one. So f of x equals 2x.
F of x equals 1. 2, I mean. I know how multiplication works.
So my derivative is 2. Is that ever 0 or undefined? No. What's wrong with that?
Yes, sir.
Doesn't have to float in.
Okay, is this a closed interval?
Oh.
I said between 0 and 1. So we know there's no critical points right now. So my max and min have to happen at endpoints. If I put in 0, we get 0. But when I put in 1,
You too.
we get 2. But if it's not equal to, what would you?
Open.
It would be an open circle. So does this have a max?
No.
No. So on this one we see 0, 0 is my absolute min. There is no absolute max. Why?
It's not more than that. There's no. It doesn't end.
It doesn't end. There was no closed interval. So I put this intentionally to show you our strategy only works if you have 2 endpoints. Okay, if one of them is not an endpoint, then it can't guarantee anything. Alright, there were 2 requirements for this to work. It has to be closed interval and what kind of function?
Continuous.
Continuous. So if I give you this one,
That's not.
it's a closed interval.
That's not continuous.
Probably not continuous, is it? If you think about the graph,
Circle and left.
if x is 0, we get out 1. This, if you put in 1, you get 1 between 0 and 1. If you put in 1/2, you would get 2. If you put in 1/3, you get 3. And it just keeps rising because it's an asymptote there. So this one's not continuous. So will I have to have a max or a min? No. Which one does this one have?
Local.
an absolute min twice actually.
That doesn't seem right.
When do we hit our lowest points?
0. Oh, it does. 0 and 1.
0, 1, and
1.
1, 1. There's no max here. Okay, and the reason I put these last two on there is to illustrate it has to be a closed interval, it has to be a continuous function. Otherwise our strategy does not work. Alright, enough of ones that it doesn't work on. Let's actually do some that it will.
Ones we can do.
Now we know what to look for. It has to be continuous, closed interval. Alright, so if I ask you to find this max and min, we need our derivative. As it's written right now, what would I have to do?
Distribute.
Yeah. So 3/5 times 30. Don't you grab your calculator? Think 30 divided by 5 is
6.
6 times 3.
It's 18. Wow.
You guys are so smart. Thank you. So our derivative is 18x minus 6/5. I'm sorry, not 18x, 18 minus 6/5 x. Is that ever undefined?
No.
No. So I just need to know when. 0. Okay, let's try it without a calculator. If I multiply by 5 over 6,
90 over 6, which is
or do, what's 18 divided by 6?
3.
Times 5.
15. That's so much easier, but I didn't want to do it that way.
You wanted the challenge.
I wouldn't have done that.
So my critical point is at 15.
Now we plug that back in the original.
I have to plug what numbers into my original?
15.
0,
And 30.
15, and 30. So if I put in 0, I'll do that one again. 15 gives us 135.
135.
30. So what is my absolute max?
135.
And what happens with the others? Yeah, so we have two absolute mins there. Okay. I'm going to stop. What I want you to do, I'm going to